Hi everyone, my name is Sanjay Chouhan and welcome to my YouTube channel. So in this NLP series, this is the fourth video and here we'll discuss the case study, our first case study. And in the first case study, we'll focus on what are topics that we have covered in our previous videos. So we have covered text pre-processing and text representation or vectorization. So in this case study, we'll focus on those two topics. And the first case study is for sentiment analysis. So we'll perform sentiment analysis in this project. Our main focus will be the NLP stuff, and we won't focus on the machine learning related things. And we assume that you are aware of basics of machine learning and basics of Python. So our focus won't be towards the machine learning. So for this task, we'll be using Kaggle. Kaggle is a repository of dataset. Here you can find lots of different kind of dataset for your machine learning or data science based projects. And we'll be using Kaggle notebook and Kaggle dataset. So the dataset that we are using is IMDb dataset. So IMDb dataset of 50K movie reviews. So here we have 50,000 movie reviews. So you can start this notebook by going to the dataset uh, page, and then if you click on code and create notebook, it will create a blank notebook. The first cell will be filled. So this cell is filled by the Kaggle itself. So here they have imported the basic stuff like NumPy and pandas, and they have also uh, displayed the files present in this Kaggle input directory on this notebook. So we can see that we have the IMDb dataset file here. So we have this CSV file which is having the data for IMDb, and it's present in this location. Okay, so let's load the dataset. So we can directly use the path, and you can use pandas to read the CSV file. So let's look into the basic EDA. Our main focus is on NLP and basics of NLP. I won't do bit deep EDA analysis here. I'll do basic EDA analysis just to understand the data. So we see that we have two columns and 50,000 rows. So we'll be only processing 10,000 rows because that's too much data for this small task. You can use all the data set and do your analysis, but it will take time. So I'm just sampling 10,000 data points from this. So we have sampled 10,000 data set, and when we print the head of this data frame, we see that we have this review column and the sentiment column. And in the review, we have reviews for the movies, and in the sentiment, we have a negative and positive sentiment. Let's see if we have any null values. So when we use df.info, we see that all the values are present and there are no null values for both the columns. And let's see how many positive and negative sentiments are there. We can use the value counts method from data frame. So we see that we have 5,015 positive sentiment and 4,985 negative sentiments. So the data set is balanced because we have almost same number of data points from both the classes. So this is a binary classification where we have positive and negative class, and in this classification task, we see that the data set is balanced. So the sentiment column contains this text, positive and negative. For the model building, we'll need the number instead of text. So we are converting this text to number, and we are creating another column called df output. Sorry, the column name is output. Where we're storing in this df, that is data frame only. So what we are doing is we are converting positive to 1 and negative to 0. So wherever we are having positive in the sentiment column, we are saying 1, and wherever we are having negative in the sentiment column, we are saying 0. Then we are creating this TF output column. Just for sanity check, we can see that we are having same number of ones and zeros as as the positive and negative classes you see in the sentiment column. Let's look into the length of the reviews. So we can do we can just split the reviews using the split function from the string, and it will split based on the white spaces. So and then we are splitting the review, then we are taking the length of the array that we get after splitting, and we are having this lambda function, and we are applying this lambda function to this review column in the data frame to create the length column. So it will create a column called length where we'll have the length of each reviews, and length is calculated by dividing splitting the review based on white spaces and counting the number of words. So let's look into the statistics of the length. So here is the statistics of the length column. We can use the describe function from data frame to describe it. Our main focus would be the min, max, and then these quantiles. Okay. We see that the minimum is 10, so we are having at least 10 words in the review, and we are having a max of 2,125 words. We see that 50% of the reviews are of less than or equals to 172 words, and 75% of the reviews are of less than or equal to 278 words. So most of our reviews are around 100 and 200 words only. Okay, so that we have done the basics of EDA, let's look into the first step, text pre-processing. So we have discussed the text pre-processing in our first video. So I hope you remember it. So we are importing the required libraries here. We are importing regular expression, string, NLTK, beautiful soup, and stopwatch from NLTK. So here we have downloaded the stopwatch. So our first step in the text pre-processing is cleaning. So first we have downloaded the stopwatch. So in this stopwatch we'll have not as well. So we'll be removing not. So here we are removing the not from the stopwatch set of stopwatch. So this will remove the not. So that so let's suppose we have two movie reviews. I did like the movie, and I did not like the movie. If you remove the not from both the sentences, the sentence will become same. So we are removing, if you're removing not, then we are losing a very important information from the sentence. So it's best to not to remove the not from the sentence or the reviews. So we are removing the not from the list of stop words. And we'll do one more thing. You see that we are also removing uh, don't, didn't. So what will happen is that if you are having like I did like the movie or I didn't like the movie, and then if you're removing I didn't and did from the sentence, right? Did and didn't are also present here in this stop words. So if you're removing did and didn't from the sentence become I like the movie. So here also we are losing important information. So what we are doing is that we are expanding the anti-contractions. So wherever we are having an apostrophe T to like it for you will have this in didn't, isn't, couldn't. So we'll replace this an apostrophe T with not. Basically space and not. So we are having this regular expression for this. Let's see in action. So let's suppose we have this sentence. I didn't like the movie. So once we run this, once we pass through this function, it will convert this sentences into I did not like the movie. And now when we remove the stop words, this did will be removed, but not will not be removed because it's not present in that list of stop word. Whereas earlier, if you're not doing this anti-contraction, then the whole detent will be removed, and so that's an issue. So next thing is the pre-processed text. We have seen this function already. I'm just adding this empty contraction part just before the removing stop words step. We have seen this like we need to convert the text into lowercase. So we are converting the reviews into lowercase. We'll parse the HTML tags. So the reviews will contain HTML tags because those are extracted from the IMDb site. So obviously it will have some HTML tags. So remove the HTML tags. We'll remove any kind of URLs, and we'll remove emojis, punctuation marks, numbers, and then stop word. So we've seen why I need to run through all of these steps earlier. So we're running these steps, and basically we'll use the apply function of data frame to apply this whole pre-processing function over these reviews, and we'll create a separate data frame called clean review. So now if you see here, cleaning the review, we're having earlier we were having this review, right? After cleaning, we see that everything is converted, and we have removed stop words and everything. So let's see an example here. In this example, we have this the HTML tags, and after cleaning, so this is the original review, and this is the clean review. After cleaning, we see that the HTML tags are gone. Everything is converted to lower form or lower text, and we are also not having the stop words. So next step is the text normalization, where we use either stemming or lemmatization. So either one of them is fine. So here I'll be using lemmatization. If you're using stemming, then we won't be able to use the Word2Vec because if you're performing Word2Vec, the word needs to be from dictionary. So if you are using stemming, the word converted or the stemmed word might not be in the dictionary, as we have seen earlier. So stemming is not recommended if you are planning to use Word2Vec. So that's why I'm using the WordNet limitizer. So we have seen already how to use the WordNet limitizer. And we are tokenizing the sentence based on word using the word tokenized from NLTK library. And then we are limitizing each of the word. Here I have given POS as P for verb. You can dynamically give, but this will also work fine. Yeah, we have already seen this. So we are running through each of the word in the list of words, and we are limitizing each of the word and creating this lemmas array. And we'll join this list with one blank spaces, and we'll get the lemmatized version of the clean review. So this is the function. We'll apply this function over this clean review column. So we are using again that data frame apply function here. So you'll see that this is the normalized review. So we see few of the words are converted back into present tense. But yeah, this is a normalized and clean version of the review. And we'll be using this for our model building. Now that we have done the text pre-processing, so let's, before proceeding further, we need to create train test split. Here we'll be creating three split, train, test, and validation. So we'll be using the train test split function from sklearn model selection. What we are doing is we are having 70% of the data in train, and we'll be having 10% of data for validation and remaining 20% for test. So we are using this train test split function, and we are providing the data frame, the original data frame. We are saying that the train size should be of 0.7, that means 70%. So it will give us two different data frames. First one is for train and second one is for test. So the train DF is the training data frame, and then which is having 70% of the data. And this is a temp DF where we are having 30% of the data because we will need to split this data frame into again you need to split this data frame into well listen and test. So we will be calling this train test split again with this temp df. So what we'll do is we'll pass this temp df in this train test split. We'll see that we'll say that test size is 2 by 3. So what will happen is that out of this 30% remaining in the temp df, 20% will be used for test. So this is the test df. 20% of the data will be available in the test df, and remaining 10% will be available in this well-designed df. Because we are using test sizes 2 by 3, so the 30% remaining 30% data will be divided like this. You can check the sizes of each of the data frame. We are printing the length of each of the data frame. You can see train is having 7,000 data points, while lesson is having 1,000 data points, and then the test is having 2,000 data points. Now that we have splitted the data into train, validation, and test set, let's look into text representation or text vectorization. So the first one is the BEGA words. So we have seen already, like we can use the BEGA words from from sklearn using the count vectorizer class. We importing this class. We are initializing the class with this parameter. So min df is 3. That means if the word occurring in less than 3 data frame, then it won't be used. And max df is 0.95. That means if the token is occurring in more than 95% of the documents, then also it won't be used. We are ignoring the very frequent and very rare words or tokens, because the very rare words might be because of mistyping, and very frequent words might not be very important. So we are removing those non-important words from the word using these parameters. And then we are calling the fit transform function on this vectorizer object. And we are calling the fit transform function from this vectorizer object. I will pass the normalized review of the trained here. Here we are not only transforming, we are also fitting. So that means when you are using fit transform, it will create the vocabulary from this data set only. So we need to use the trained data frame. And then we can transform the other data frame. So let's look into the shape of this trained data frame. So here we see that the shape of this X train, which will be the input to the model, it's of 7,000 by 16,174. So we are having 16,174 columns. That means our input will be of this dimension. Okay, so for each of the reviews, and the vector representation is of 16,174 length. So which is a very big vector to represent the reviews. And we have already mentioned while discussing that BEGA words will create a vector representation of tens of thousands dimension. But you'll see that the vector representation for BEGA words will be very sparse. So if we print the first representation from the extreme, you'll see that we are getting compressed sparse row, and this is called CSR as well. So CSR is a format to store sparse matrix. Basically, in CSR, what we do is we store the non-zero values. So if we know that vector or matrix is very sparse, where we are having lots of zeros, we only store the non-zero values. So to store the non-zero values, we store the location or position of that non-zero value and then the value itself. So we see that out of this 16,174, only 34 are non-zero. So with here you can see with 34 stored elements, and so that means only 34 are non-zero out of this 16,000 columns. So let's transform the others as well. So here we are transforming the validation data set. So we'll use the val_df data frame. We'll use the same column, normalized review. See here, we are not using the fit transform. We are only using transform because we have fitted the training data. We have fitted the training data means the vocabulary is created based on the training data. So we fitted the training data. We need to transform the other data set using the fitted object. So that means we'll use the same variable or same instance. So we are using the vectorizer instance, and we are transforming the validation data frame. This will create the xval array where we see that for all the 1,000 reviews, we are having vector representation of 16,174 dimension. So it's same as the dimension will be same as the training dataset because we are using the same instance for transforming. And similarly, we'll transform the test data frame as well to get the x test variable, and the shape will be same. So that 2,000 is for 2,000 rows. That means 2,000 data points, and then the dimension or representation will be same. So let's build a model. So here we'll be creating the outputs as well. So we have created the inputs, so and we have stored them in x underscore val or x underscore train, right? We need to create the output variables as well. We have the output in the train df, validation df, and test df. We'll just store them in y train, y validation, and y test variables. We are getting the values from all the respective data frames. Okay, so we have created this variable for outputs, and let's build the model. So we'll be using the logistic regression model from sklearn to build this model, and we'll be also using the accuracy score from sklearn library. So we have imported both of them from sklearn, and I won't discuss much about this model building process because in this series we'll be focusing on NLP. Probably in other series we'll discuss about the machine learning stuff. Basically, we are getting this model, and this is a linear model, and this is performance metrics. This is called accuracy score, and we'll be doing hyperparameter tuning. Basically, the model have hyperparameters, and the hyperparameter that this logistic regression model have is C values. So we can try out different C values and see which of the C value is performing the best given this data set. So we are trying out a few different C values. We are trying out these 5 C values, and what we are doing is that we are keeping track of the best accuracy that we are getting, and for which C value we are getting the best accuracy, and what is the best model. So you'll see in this cell that we are looking through each of the C values. We are creating the instance of this class. We are passing C equals to C. So we are passing the C parameter, and this max iteration and the random state is going to be same. We are only trying out different C values. So after creating the instance of this class, we are fitting using the train data. So we are passing x train and y train in the model. So we'll use the model.fit function here to train the model. So this will train the model using this hyperparameter and this training data. Once we have trained, we are getting the prediction for the X validation. So we'll call the dot predict function from the model, and it will give us the prediction for this validation. So we are passing the X val, that is the input data for validation, and we are getting the Y val prediction. So we are storing this the predictions for the validation data in Y underscore val underscore pred. So we'll calculate the accuracy score on this validation dataset. So we'll call this function called accuracy score, where we are passing the original output of the validation dataset. So y underscore val is for the original output values for this validation data, and this y underscore val underscore pred is for the predicted value from the model. So we'll pass both the original and the predicted value to get the accuracy score. So the accuracy score are present in decimal, so we are multiplying with 100 to get 2%. So here we are printing the validation accuracy. So this if block will make sure that we are keeping track of the best validation accuracy and so the best C value and best model. So when you run this, you'll see that we are trying out different C values, and for each of the C value, we are having different validation accuracy. We say that the accuracy is increasing as we try out different C values, and it peaks at 0.1 C value, and then it declines. So our best C is 0.1, and our best model. So if you print the best model, you'll see that logistic regression model with C of 0.1 is having the best model. So we have access to the trained model. Now we'll be using this model to get the accuracy score on the test data. So similar to the what we have done for the validation data, we'll use the best model and call the predict function, pass the X test to get the Y test spread. So this will give the prediction for the test data, and we'll use the accuracy score function, and then there we'll pass the original output from the for the test data, and then the predicted output for the test data. So this will give us the accuracy, and here we are multiplying with 100 to get a percentage. We see that we are getting test accuracy of 86%, which is a very good number, given that we have done this with very minimal work. So we are able to correctly classify 86% of the data in the test. Okay, let's look into some other techniques. So here we have used Word in this example. Let's now try with the Word2Vec. So we'll load the Word2Vec model, the Google model, which is the Google News 300 model. You can directly download from Gensim. So you'll be using this cell to download the model from Gensim. So this will load the model Word2Vec Google News 300 model, which will give you the vector representation of each of the word of dimension 300. And we discussed that this only gives you the vector representation for each of the word. So to get the vector representation for whole document, what we need to do is we need to get an average of all the vector representation of all the words. So we are creating this function called sentence embedding. So basically here what we are doing is converting everything to lowercase, and we are tokenizing text. The text will be the review. So by what tokenize, it means it will tokenize each of the word, and we'll have the list of words. So we'll go through each of the word in the list of words, and if the word is present in the Word2Vec model, then we'll get the vector representation for the word. And we are storing everything in this word vectors list. Once we've gotten all the vector representation for all the word present in the review, we'll calculate the mean or the average using this numpy function. So this will give you the average Word2Vec representation of the sentence or the review. So to run this function, we'll be using the data frame apply function. Okay, so we'll be calling this train df apply function, and this will be applied on the normalized review column only. So we'll use the normalized review, and there we'll apply the sentence embedding function. It will convert the whole review into embedding using the average Word2Vec technique. Here we are just converting the train data set into 2D data frame. You will see that the shape of that, sorry, not the 2D data frame, we are converting to 2D array, and the shape of this 2D array is 7000 by 300. So 7000 is the rows, that means the data points, and 300 is the columns, that means this is the representations. So we saw that the Word2Vec gives us the vector representation of length 300. So that's why we're seeing 300 columns here. So we need to do the same for the validation and test data set. So here we are getting the xval and xtest as well. And then we'll do the same trading method. We'll follow the same trading method for this Word2Vec example as well. So I have just copied the same code from earlier. Here also we are having different C values that we're trying. And similar to that BoW word, here also we are training the logistic regression model with different C values and then printing the validation accuracy for all the C values. Choosing the best model and then running the best model for the training data, sorry, test data to get the test accuracy. So this whole block of code will do this. So we'll see the output here. So see that for each of the C values, we are having different validation accuracy. As earlier, it is increasing from 79.4 to 85.5 and then again decreasing. So the best C value that we are having is C equals to 10. And with C equals to 10, the test accuracy is 86.25. So which is similar to what we have seen for the BoW word. So this is what we get for the Word2Vec model. Now let's look into the other one, the sentence BERT one. So we'll import the sentence transformer class. Okay. So here we are importing the sentence transformer from the sentence transformers library. We are initializing the model. Basically, we are using this all MPNet based V2 model, which we discussed in our earlier video as well. We are getting this model and we'll encode all the reviews. So we are encoding the normalized review for the train data to create the strain variable. So we are storing all the encoded or vectorized reviews in Xtrain for training data. And for validation data, we are saving everything in, we are storing everything in XVAL. And for test data, we are storing everything in Xtest. So here we have used the normalized review. And once we run this for model building, this is the same code that we have seen earlier as well. Here also we are trying out different C values, including the initializing the model with different C values, then fitting the model on the training data, getting the validation accuracy, and choosing the best model based on the validation accuracy, and then getting the score on the best model. So here also you see that the validation accuracy is increasing, and then it peaks at 86.5, where the C value is 10, and then it decreases. So best C is 10, and the test accuracy we get is 86.55. So till now, whatever we have seen is we're getting that we're getting a accuracy of around 86% of accuracy we're getting on the test data on all of the method that we have tried for vector representation or text representation. But for this sentence part, I think I mentioned in the last video as well that we don't need to run do any kind of cleaning and the normalization for sentence BERT, because the sentence BERT or the BERT-based model are trained using raw data. So that means you can directly use the raw data, and we should use the raw data instead of cleaning too much or normalizing them. So let's look into another variation. So let me scroll down. So as BERT works better with raw text. By raw text, I mean you don't need to convert to lowercase, or you don't need to remove words or punctuations. You don't even need to remove emojis, and no need to do any kind of limitation or anything. But it's always best to remove links and remove the HTML tag. So here we are doing two things only. We are using the Beautiful Soup library to remove the HTML tags, and then we are also removing the any of the URLs. So this will remove the URLs. So these two steps are necessary. Other than that, we don't need to do anything. So we'll run this pre-processed text function for each of the reviews. So we have the train DF where we are having the training data, and we are applying this pre-processed text on the review, the original review. So here we are applying this pre-processed text on the original review, and then we are getting the strain, and we are encoding this train data using model encode function from this model. What's the model name? All embedding-based video. So we are encoding all the training data as before. So we're getting this extract. Similarly, for validation data also, we are pre-processing it using this technique, and then we are encoding. And same for the test data as well. So now we have new extract, X validation, and X test, where we are only performing these two steps in pre-processing, and then we are building the model. So similar to earlier, we are building the model using different C values, and we are trying out, we are building this model, and we are checking the validation accuracy for all the C values, and whatever is the best, we'll be using that best model to get the test accuracy. So here we see that the validation accuracy is increasing from 83.5, and it peaks at 90.10, where we are having C equals to 10. So the best C value is C equals to 10. And then when we see the test accuracy is 89.50. So we see a jump of about 3%. Earlier we were seeing the test accuracy around 86. Now we are seeing it as it is at 89.50. We see that we see a 3% jump just because we're not using the normalized data here. Earlier in this SBERT example, we are using the normalized data. And when we move from the normalized to original raw text, we see a 3% jump. So as I mentioned earlier as well, the SBERT or the sentence BERT is the best one among all of the text representation techniques. We can see here as well that SBERT is producing the best result, and we don't need to do any kind of pre-processing. And thanks for watching. In this case study, we only focused on the two topics, text pre-processing and text representation. So it was short, and our main focus was to just showcase the NLP related stuff. So we have not gone deep into model building. And if you have any queries, then you can comment. I'll get back to you in the comment. Thanks again.